Okay, so our final topic before we read our quiz is on saturation. You guys actually already know a little bit about saturation, I imagine, because you've been taught a little bit of this already in chemistry. Plus, you probably know this word from other fields. So, like in a non-chemistry perspective, what does saturated mean? What if I told you that that sponge was really saturated? What does that mean? Or like, what if the soil was saturated? Yeah, it's wet. Like it's absorbed a lot of whatever it is it's tried to absorb. Does that make sense? Right? You probably heard that the word saturated before, right? Oh. So I mean, if you were to think of a plant having saturated with water or a sponge being saturated, it's full. Well, full of what? Well, in those examples, water. Well, when we make solutions, if we have what's considered to be a saturated solution, it's absorbed a lot of, well, what do solutions absorb? Solute. Yeah. That's really the concept I want to talk about today is what happens when you have a solution that has absorbed so much solute that really it's considered full, quote unquote. Because you can actually have solutions that you poured so much solute in there that it's reached its capacity. And that's the word I really like to use when we talk about saturation. The idea of like every solution has a capacity where at some point it no longer is able to dissolve anything more. And before I come back to the slide here, I want to skip ahead to a visual picture, an analogy I've used in the past. Okay. What is really happening when something dissolves? If we were to look at it on a molecular level, what is actually occurring? And here, oh my goodness, where is it? Here it is. If you want to just fast forward a bit or just look here. Here's a picture that maybe was describing what's happening when something dissolves. Okay. You've got an ionic solid. What are ionic things made out of? I don't know, anions and cations. That was a poor choice of color. You can't see the negatives on there. You get what I'm going for here, though, right? Positives and negatives. Why do the positives and negatives separate? Water, right? If there's enough water, water literally overruns all of these particles and rips them apart. The analogy, I use so many analogies in chem, by the way. The analogy I give is you guys right here, if you wanted to sit by your friend, no one's stopping you. You're an ionic solid. Right? Throw 700 second graders in this classroom. I mean, in general, I am bigger and stronger than a second grader, right? But I don't think that I could take on 700 of them, right? Like at some point here, I wouldn't be able to sit next to my friend anymore if there were that many, right? That's really what's happening with water. There's so much water, and water is polar, that it's able to just literally rip this thing to shreds. And so, although this guy right here is negatively charged, and this one right here is positively charged still, and they would love to meet up because positives and negatives attract. They can't. There's just that much water. Fair enough. But there is a capacity to where if we just kept adding more and more ionic solid, if we had so much ionic solid, then maybe not all of it could get ripped apart. Because really, at some point, the amount of solvent has to matter. You get what I'm saying here? If we didn't have enough solvent, then maybe it doesn't all dissolve, and maybe there's some stuff left over. And you guys have already seen this before on this table right here. You guys know this table from your data booklets? Right? In a way, we've already talked about how things in this top column up here, they're aqueous, which means that they have a high tendency to dissolve. They will almost always break apart into pieces. But if something falls into the bottom category, like down here, we say that it's like solid or slightly soluble is the word we would use, where we can dissolve some of it, but these things right here, it takes a lot of water molecules to rip them apart, right? Because really there is a capacity. And so we actually, what we're going to talk about today is how when there's solubility, it's actually a numerical value. Okay? If I talk about solubility, it is the concentration of when you have a saturated solution. And saturated, a better way of thinking about it is, this is when it's full. You have put exactly as much solid in as you can. And if you try to put more solid in the solution, it can't dissolve anymore. It has reached its capacity. Does that make sense? Another example I like to give, does anybody know what a governor does on a car? In theory, without a governor on your car, you could just keep speeding up and go faster and faster and faster. But most cars have a device on it that basically, once it reaches a certain speed, it cuts off the engine so that you can't go, like, say, 300 miles an hour. Does that make sense? It's a capacity. It says, can you please have your attendance done in the next 5 minutes? Junior high teachers, please have your attendance done in the next 5 minutes. it basically makes it so that you can't drive your car like infinity fast. Does that make sense? Because in theory, you just keep hitting the gas, and it keeps adding more and more gas to the engine. It keeps moving them faster and faster. But I mean, for safety's sake, most cars usually kind of cut off at a certain speed, right? Whether that's 160 kilometers an hour or 200 kilometers, whatever your car happens to be, right? But does that make sense? That's a governor on a car. There's a capacity to how fast we let you go, right? Well, same thing on here. All solutions have a capacity at which, if you were to add more solute, I'm going to find another picture here. Just stay on your slides, though. There's a picture. Here would be an example of an unsaturated solution. I add the solid into the beaker, and it all dissolves. It's not full yet. But see this one right here, if I added 40 grams inside here, see how there's like a little bit of precipitate sitting on the bottom? Well, this would be an example of a solution that is past its saturation point. It is full. Does that make sense? So going back to my first slide here, the point I need to make, if I'm not doing a very good job of it, is the solubility is the concentration when it's full. Right? Every solution has its own capacity. For example, salt might be full at 10 moles per liter, whereas sodium phosphate might be full at 3 moles per liter. And potassium iodide might be full at 7 moles per liter. You get what I'm saying? Every compound reacts slightly differently. And one of the reasons why is it has to do with particle size. Okay, I've got that listed up here. As particle size increases, it's actually easier to dissolve it. And that's because, think back to when I finished those examples I gave there. If you have a large particle, you probably have fewer of them. Say that again. If you have a large particle, when you dissociate it, you have fewer of them to like break apart. And so sometimes it's actually easier to dissolve bigger particles because you need less water for it. If you have a whole bunch of small particles, you need lots of water for each of the small particles. You get what I'm saying here? So if you have bigger particles, in general, it probably means you have fewer of them. If you have fewer of them, you need fewer waters to separate them. So therefore, it's actually easier to dissolve because you have extra waters left over. Anyways, another definition I have down here then, a saturated solution then is the solution in which no more solute will dissolve. Okay. However, I keep going in my definition here though, at a specified temperature. Think of making hot chocolate. I know we like drinking our hot chocolate hot because it tastes good, I guess, right? But another reason why it works well is that at higher temperatures, things dissolve better, don't they? Right? I mean, that's why we make our tea hot, our chocolate hot, our coffee hot, right? We don't brew it in cold water and then heat it up later. We brew it in hot water. What do warm molecules do? Like what happens when molecules are hotter? What's happening to them? Yeah, they're vibrating faster, they're moving faster. And so if I go back to this example right here, if they're moving faster, all of these water molecules have like they've drinking a caffeinated drink and they're really excited and they're buzzing around everywhere, right? They have more ability to break up the ionic solid. So at a higher temperature, you can actually dissolve more stuff because these water molecules are buzzing around a little bit quicker. Does that make sense? So, okay, let me keep moving here because I'm taking too long on this. Long story short is that on that solubility table that I've shown you here, there's actually some numbers. And for the most part, up until today, I've never talked about that number before. But there's actually like kind of a natural breaking point for most substances. It's 0.1 moles per liter. Okay, and I want to go to this table here and talk about it because you probably have never really cared much about the fact that it actually states something on this table. I want to talk about that now. Everything in the top category has a high solubility, meaning that it is much higher than 0.1 mole per liter capacity. For example, I'm just making these up. NaCl might have a capacity of 12 moles per liter. Na2SO4 might have a capacity of 3 moles per liter. All these things have a very high capacity. Does that make sense? And due to their high capacities, they ended up in the top column. There are some things, though, that have a very low capacity. They get full very quickly. Like, for example, this one down here, rubidium perchlorate, perhaps its capacity is 0.03 moles per liter. Okay? And it just happened to work out quite nicely that as we look at the capacities for every single solution here, there was a fairly natural divide at 0.1 moles per liter. So that's how the chart was made. Everything that's well above it went into these categories up here, and everything that was well below was here. And it was very fortunate there was a natural divide. However, not everything was perfect. It's not like every single substance was like that. So there are some substances that actually have a solubility capacity around 1.1 mole per liter, and they're just exceptions. But in general, that chart then will let you know whether things have high or low solubilities. Does that make sense? So I don't need you to actually know the exact number, but what I do need you to know is whether it's above this number or below this number. Okay. I talked about temperature. This is actually what we're gonna do in our lab tomorrow, though. Solubility in general should increase as you up the temperature. Take a look at this graph I've got right here. Here, the solubility of all of these compounds is slightly different. And rather than measuring it in moles per liter, by the way, this one here measures it in grams of solute per grams of, I don't know why this is HO. This should be H2O, grams of water. So rather than measuring it in moles per liter, it's been measured in grams of solute per 100 grams of water. And this is what we're going to do tomorrow. If you were to take, like we will tomorrow, potassium nitrate, this one right here, if it were to be at 0, you could shove about 13 grams in 100 grams of water. But if you up the temperature to, say, 10 degrees, well, now you can put 20 grams in that same beaker of water. And if you were to up the temperature to, say, 50 degrees Celsius, now you can put 90 grams in that same beaker of water. This is actually our lab. What we're going to do is scale it down, though. I'm going to give you a test tube. We're going to measure out a little bit of water, not 100 grams, because I don't have the ability to give you, like, 60 grams of this stuff. That's like an entire bottle. We don't have the funds for that. So we're going to scale it down. I'm going to give you, say, 5 grams of water. And I'm going to ask you to try to put 1 gram of solute in it. And then you're going to heat it up until it dissolves. You're going to record its temperature. Then you're going to put in 2 grams of solid. Heat it up until it dissolves. Record its temperature. Put in 3 grams of solid. You kind of get where this goes here? And what you're going to be able to do when you're done is you'll be able to plot a graph. And you'll notice that every single one of these graphs, as you up the temperature, the solubility increases as well. Does that make sense? Now, what's unique about these ones here, especially for the guys in grade 12, because we're going to do this in math, these things either follow a straight line graph. You guys remember what it's called when it's a straight line graph, what the name we give it is? Linear, yeah. It either follows a linear graph, or it follows a curved graph like this. We haven't covered it yet. Do you guys know what I'm referring to, though? We did it in physics. That's it. It's exponential, yeah. So some things happen to follow a linear graph where it's very consistent and you can almost find a slope to it. Some of these things actually kind of accelerate as you keep going. Okay. But the important part here is as you heat things up, the capacity for how much solute you can shove inside gets higher. Okay, what else can I talk about here? So there's a lot of solutions then that have solutes, but they're at maximum concentration. Right? If you are full and you try to add more solute inside, what's going to happen? Well, it won't dissolve, right? Like literally, it will just sit there. It will remain in a solid form on the bottom. You guys probably will actually see this if you were to make, say, Kool-Aid. Okay. Ever notice how you pour the Kool-Aid crystals into the beaker, whatever you're making it? You don't make it in a beaker, in a jug. You stir it up, right? But like you let it sit for a minute or two, and then you notice there's like a little bit of crystals in the bottom. Well, that's because you're past its capacity. It's now saturated. You know what I mean? It's a full solution. There's no point in adding any more crystals because they won't dissolve. They'll just sit on the bottom of the container, and you'll just be drinking solids. Right? So I do want to point this out here. What happens if it's not a solid in liquid, though? What if you have a gas? Well, gases will bubble off the surface of the solution. And this actually happens every time you open a can of pop. You crack a can of pop. What you have inside there is a pressurized solution. What's the solute? Carbon dioxide, yeah. And as you open it up, it's no longer a closed system, it's now an open system. And all of the excess carbon dioxide, they just keep shoving more and more carbon dioxide inside, right? But as soon as you open it up, it's past its capacity. The carbon dioxide bubbles off the top. Does that make sense? So, I actually talk about that right here as well. I talk about pop here. Solids actually have a higher solubility in water at higher temperatures. Gases actually are weird though. Gases have a higher solubility at lower temperatures. I want you guys to know this here. It's strange, but gases are actually more soluble if you cool things down. You can actually shove more gas in at a colder temperature. Gases also are more soluble at higher pressures. So this is again the carbonated drinks thing. You can shove more and more and more carbon dioxide into a bottle of pop if you pressurize it. But what happens as soon as all the pressure is gone? Well, now it's way over capacity, and that's why it bubbles. Right? Now, if you shake your can of pop, what are you doing? You're adding even more pressure to it, right? And so by adding even more pressure to it, even more carbon dioxide is going to dissolve. And as soon as you open it up, it all comes immediately out, right? Okay, here's another picture kind of illustrating what I've mentioned before, but hopefully I made my point here. This right here, you would consider this unsaturated. It is not yet full. This one right here is so saturated that there's something left over here. Do we normally want solutions with a little bit of like sludge in the bottom? How do we get rid of it? Okay, you could play a game of, well, try to add a little more water. But what if you add a little bit too much water and now it's no longer at its capacity anymore, right? Like what if you were to add a little more water to this, but you added like 2 milliliters too much? Anyone have any other ideas as to how to make this exactly saturated so that it's not, what was that? Okay, but what if you heat it up a little bit too much and it goes past capacity? Or what happens when it eventually cools back down again? Well, really what you have here is no longer a homogeneous mixture. Remember like the difference between homogeneous and heterogeneous? Okay. How do you separate a heterogeneous mixture? Things that visibly have two components to it. Does that make sense? If you can visibly see the components, find some way to separate them. The best way is a filter, right? I mean, otherwise you could literally just, this sounds dumb, but take your spoon, go down to the bottom and just scoop it out, right? Right? A filter is actually probably much more technical, but does that make sense? Okay, it's actually possible for solutions to become what are called supersaturated solutions. Now, this isn't something I'm going to test you on, but it's super cool, so I want to explain it real quick here. It's actually possible for you to make something go past its capacity if you mess around with temperature or pressure. I already mentioned pop. Pop is actually past its carbon dioxide threshold. But the reason why it works is that you just highly pressurize it, and then it's able to be stable. Okay? Another way you could do things is you could just heat things up, add more temperature to it. And so here's how a supersaturated solution works. I'm just going to read off my slides for once. What you do is you'd add a high amount of solute to a solution at a really, really, really high temperature. And under that high temperature conditions, the solution is just saturated because at that temperature, that would be considered normal, right? As you up the temperature, you can have more solute than solvent, right? But here's what you do. You flash freeze it. Okay, like you instantly drop the temperature. Okay, all at once. Sometimes the solution is able to hold more solute than it should, and it manages to stay in just like a fragile state of equilibrium. Okay, I'm going to go back to this picture here. What's really occurring is that all of these water molecules are trying to like pull apart all of the solids. And if these water molecules have enough energy, they're able to do so. What if you instantly remove all of their energy? Well, if they were in a perfect state of balance and they were able to be like holding off all the invaders or something like that, they might actually be able to maintain that for a little while. But any sort of movement, if you just bump the solution, or like sometimes it becomes unstable, it'll instantly, the term we use is fall out of solution. And I've got a picture here where this would be an example of an oversaturated solution. It's supersaturated. There is so much solute in there that it's past its capacity. And if it were just a bump, you'd all of a sudden see it crystallize. And it's super cool. This is actually what you guys are going to see in our lab tomorrow. I'm going to have you guys add solute, and like you're going to have like this much water, just a little bit. And first you're going to put in 1 gram, and it'll dissolve, no problem. Then you'll put in 2 grams. It won't dissolve, so you're going to heat it up, and eventually it will dissolve. and eventually you'll put in 3 grams and 4 grams, and eventually you'll be amazed to discover that you've put in like this much solid and like this much water, and it seems not possible. The only reason why it works though is because you heat it up. Well, what happens if you redrop the temperature? What happens if you cool it back down? Eventually, you'll actually watch crystals grow on your test tube. And in your lab, as soon as you see crystals grow, that's the temperature we want, because that's the temperature at which it was full. Does that make sense? So I'll show you it tomorrow, but hopefully that gives you kind of an idea. It's actually really cool. It's like watching snowflakes grow on the bottom of your flask because it's over its capacity, and as it cools down, the phrase you might hear is it drops out of solution. That's the phrase you might hear somewhere. Okay, so let's talk a little bit about the term we use for that. Really, what I'm describing in all of these cases here, you guys know this word. We call it a precipitate. If there is a solid that is left over that causes something to be over its capacity, that's the name we give. So I just need to make sure that you guys are familiar with how to use that table. So if I were to give you just a basic word problem here, what would happen if copper 2 sulfate and sodium sulfide were mixed? Well, copper 2 sulfate would be CuSO4. Sodium sulfide would be Na2S, because I'll catch the sulfide. If it ends in "ide," it's just sulfur by itself. What's going to happen here? What reaction takes place? Okay, so we need sodium to go with sulfate, and we need copper to go with sulfur. Okay, so which one's the precipitate? How can we tell? Well, let's just go back to our table here. I got one right here. Where is it? Sodium with sulfate. Here's the sulfate. Sodium is not down here, so that one must have a high solubility, which means it's probably the aqueous one. So this one right here is aqueous. Okay, we need to add a column to your table. You may come across sulfur once in a while, and on your table right here, there's no sulfur on it. So can you guys add a new one for sulfur, 2-? And I just have to find where it is. Sometimes I have questions that are based on an old periodic table, and that old one had sulfur on it. And every year I have to remind kids of this, and I should have brought the table out first, though. Just sit back here. Shoot. I have an old periodic table somewhere that has the sulfur column on it, but I've lost it in our move. Maybe I have an old copy of it somewhere. Data booklet 2012? No, that's not the right one. I need the 2007 one. Data booklet. Old. There it is. Okay, here's the old data booklet. Here it is. Can you guys add this column right here of S2-? Can you see that reasonably well here? In case I ever ask questions involving sulfur, just because some old questions in an old data booklet had sulfur in it, here's how it works. Lithium, magnesium, and calcium are all soluble with sulfur. Everything else is not. So just add that to your own table here. Other than that, this table in the old data booklet is the same as yours, I believe. You guys see all that? So add a column, sulfur 2-, and then lithium, magnesium, and calcium are the 3 things soluble with sulfur. Everything else goes down below. So that's lithium, calcium, magnesium. Okay, so now that we have that information, is copper one of the things that's soluble with sulfur? No, it's not. So this one is your precipitate. Okay, I always have this slide in here to remind me that I have to tell you about sulfur because it's not on the current table. So, other than the sulfur issue, you guys know how to use that table though, right? We feel pretty comfortable with it? Okay. But now you know new information, though. If I were to ask you, here's a possible question here. Which of the following could be a solubility for Na2SO4? A, 0.01 molarity. B, 5 molarity. C, 0.0001 molarity. D, 0.001 molarity. Which one could be a solubility for Na2SO4? Well, if Na2SO4 is soluble, it has a high value, right? At least above 0.1. You're not above 0.1. You're not above 0.1. You're not above 0.1. This could be the answer. Does that make sense? What would its solubility still depend on, though? Temperature, right? And so it could be 5, it could be 6, it could be 7, depending on temperature. But we know that this guy right here should have a high solubility value. This one right here, because it's solid, should have a low capacity. Sound good? Sure. Okay. Well, let's try another example here. You've got HCl and sodium hydroxide in water. Can you tell me what the products are and figure out whether they have high or low solubility? HCl and NaOH, hopefully you can do this. It makes water and sodium chloride. What's sodium chloride's capacity? Is it low or high? Go back to your table, find chlorine. The table here. Here's chlorine. Sodium's not in the bottom column, so it's high. I don't know how high it is. It could be 1, 2, 7, 11. Oh, by the way, general rule of thumb, the most concentrated solution I have in my lab is sulfuric acid. 18 moles per liter is its capacity. That is the concentratedest, that's a word, concentratedest stuff I have. So if you ever get like a concentration of like 50 or 7,000, that's off the scales. Okay? As a general rule of thumb, the strongest, it's not the right word, but the most concentrated acid I have is 18, just so you're aware. So that should give you a little bit of perspective. All right, anyways, this guy here is aqueous. Right. Whereas on this one here, H2SO4 and CaOH, you're going to have calcium sulfate and water. I believe you need a 2 here to make it work. What about calcium and sulfate, though? Back here, sulfate is here, and calcium is one of the ions that has a low capacity threshold. So I don't know what its capacity is, but it's definitely lower than 0.1. So sorry, I'm skipping around so much here. That means that this guy right here is the solid. It is the precipitate. Sound good? Cool. Okay, last concept here. Stuff in a beaker is actually not static, though. I don't know if you guys know the difference between the words static and dynamic. I mean, in general, even just your common sense on what you'd think those words are. If something is static, it's staying in one place. It's not moving. Okay? Whereas dynamic means that things are moving around, they're changing. And we actually have a phrase that we use to describe things when they dissociate. It's called dynamic equilibrium. Stuff is actually happening on a macroscopic level. Do you guys know what macroscopic means? Yeah, just you're looking at it like just with an eye, okay? Macroscopic is different than microscopic. Microscopic is like zoomed in, okay? But on a macroscopic level, if I were to look at a beaker of solution, I'll use this one here actually. If I were to look at a beaker, let's say that I just kept pouring more and more salt into this water. At some point, it's going to hit its capacity, right? I know sodium chloride has a high capacity. Let's say it's 10 moles per liter. But eventually, if I keep pouring enough in there, it's not going to dissolve. Now, to our naked eyes, you might look at it and say nothing's happening. But that's actually not true. What's actually occurring is some of these particles are breaking into ions. Some of these solid particles are actually breaking into ions. But then other ions are turning back into solid particles. And there's actually a system of equilibrium where these solids are breaking up into positives and negatives. But then somewhere else, a positive and negative came back together. And so stuff is actually still moving around. We just can't see it necessarily. Does that make sense? And so you might see this. I don't believe I'm testing you on this, but I want you to be aware of this, is that it's actually possible to have two things happening at once. Here's a dissociation equation. Here's calcium sulfate breaking up into two pieces. But somewhere else in the beaker, you might have the two pieces recrystallizing back together. You'll never see anything happening because all you see is some sludge on the bottom. But here they're breaking apart. Here they're coming together. Here they're breaking apart. Here they're coming together. The amount that's either dissolved or solid is really the same. So if you ever see a double-sided arrow, it refers to something called an equilibrium, where there's actually two equations happening at once. This one breaking apart, but simultaneously this one coming back together. And I think I have one more picture I can use to illustrate this. So if I'm making my point well enough here, there's some solid. Right? And as we put the solid in the water, the individual ions start breaking into pieces. Right? And that's what this next slide right here shows, is that, okay, well, this one comes off, and this one leaves, and this one leaves. But as soon as it hits its capacity, it's not like everything stops. It's just like, okay, stop moving. One of the reasons we know this is everything that has kinetic energy is still vibrating, though, right? Like, these molecules are still vibrating around on a molecular level. They're not just, like, sitting there just doing nothing, right? And so eventually, this guy right here might decide to pop free. Okay, and that's because enough water molecules pulled it away. But that means that over here, some water molecules say let go of this one, and it reattaches itself. Does that make sense? And so as this one finally manages to pop free, this one right here reattaches itself. And so really at the end of the day, this clump of solid that you have in the bottom, it doesn't grow and it doesn't shrink, but it's not static. Okay, so that's one thing I need you guys to understand theory-wise, is that things are happening at a molecular level, we don't notice them. So the words you might use is, as these things continue to dissolve, these ones right here might re-precipitate. You don't see anything, that's all. Okay. Quick summary of the day then. Our main concept of solubility is that solubility is a number. If I were to give you a solution, every solution has its capacity. Just like in my analogy, every car has its capacity for how fast it goes. My Volkswagen, it's a little run down, probably, and I shouldn't do this, but it probably can only hit maybe like 150, 160. It can't go faster than that. You get what I'm saying here? If I had some sort of BMW or Lamborghini, its capacity might be like, say, 220, 240 or something, right? Again, I'm not actually going to try to find it out, but you guys get the relationship here, right? Well, all solutions also have a capacity for how much solute they can dissolve. It's really based on particle size, okay? That's the main concept here. You can dissolve more if you heat things up. You can dissolve things more if you stir them, but everything has its own capacity. In general, that table that we've shown you can be separated into two halves. Things that have a capacity higher than 0.1 moles per liter and things that have a capacity lower than 0.1 moles per liter. Okay? If it's higher than 0.1, it means it's aqueous. It means it dissolves. We say that it's very soluble. Okay? But if I keep pouring more and more solid in, eventually we'll hit its limit. Okay? That's what we're going to do tomorrow. We're going to keep pumping more and more potassium nitrate into a small beaker. And the only way it'll dissolve is if we heat it up. If we cool it back down again, we'll be able to see it precipitate and crystallize. And we're going to record the temperature at which it does that, and that will give us what's known as a solubility curve, which is this kind of graph right here. Essentially, tomorrow you guys are going to make a graph, only rather than it being of all these different compounds, you're going to make it just for sodium nitrate. And hopefully we'll see that it basically keeps going faster and faster. Only the one change here is we're not going to use 20 grams in 100, because 20 grams in 100 is just too much. I don't physically have enough stuff, so we're going to downscale it. Rather than using 20 in 100, we're going to use like 1 in 5. Does that make sense? 20 out of 100 is 1/5, so we'll use 1 gram in 5 milliliters. Okay, so okay, let me talk for a little bit more, and then you guys can probably start packing up here. I just want to show you some of the things you can start working on for our unit. Has anybody printed off the lab yet? I only posted it a couple days ago. You have it? Okay. You guys, one piece of advice I would give, especially in my chemistry labs, start working on it before we actually do the lab, because you can do a lot of the questions before we actually perform it. So here's the lab. Let me talk you through it so that we're ready for tomorrow right off the bat here. Okay. If you guys have done, okay, hang on a sec. You guys in grade 11, we never did labs, right? Because I never taught you science. Okay, but you guys, grade 12, have seen my labs before. This is very typical. Here's how a lab works. I always start with a purpose, a goal of what we're going to try to do. I'm going to have you guys try to dissolve 3 grams in 5 milliliters, 4 grams in 5 milliliters, 5 grams in 5 milliliters, all the way up to 8 grams in 5 milliliters. This is like pushing its capacity well beyond what should happen. The only reason why you can dissolve 8 grams in 5 milliliters is we're heating it up. Does that make sense? Basically, if you then read through my procedure down here, you guys can read through it because I don't want to take the time for this, but the main idea is once the solute has dissolved, you want to remove the test tube from the hot water bath, you put a thermometer inside, and then the instant you start to see crystallization occurring, we need that temperature so we can plot a graph. Okay. My labs have the same setup here. Results is basically a blank page where anything that you observe, I want you to write down. So some of the things you might have observed would be how much the temperature is at the time. That's an observation. Or how much solute you've dissolved. Or how much solvent you have. All of those, by the way, are quantitative observations. I always get those backwards. You guys know what quantitative observations are? They involve numbers, yeah. But you should also include qualitative observations, things that you observe, like it turns into a white solid. Okay, so results is the place where you want to organize what you see. Okay. Then analysis is a place where you try to answer my purpose. Okay, I always have a goal for the day. So in the analysis where we want to try to answer the question posed in the purpose, the whole goal of the purpose is to try to determine the solubility temperature and sketch a graph. Okay, and so what I'm going to ask you guys to do here is to try to sketch a graph. And if you know how, because I've shown a few of you already and the rest I'll show later, we're actually going to use our graphing calculators to do this. And we're going to plot a regression on a graphing calculator, make a nice graph, and hopefully we'll discover that that graph looks just like this one right here. And if it does, our lab was successful. The next piece of all of my labs then is the post-lab questions. And you guys can actually probably start answering some of these even right now. Let's talk through some of them, because I have a few minutes here. Do you guys know the words control, manipulating, and responding variables? I know we did this in physics a lot last year. Is this something you guys have heard this phrase before? Okay, grade 12s, then help me out here. What does a control variable mean? It's something that stays the same. Yeah, every time you do a trial, it stays the same. Okay. In our lab, we are always going to try to keep one thing the same. And I can actually show you it in a visual form here. Of all of these 6 solutions we're going to make, what is the thing that's always the same? The solvent. We're always going to use 5 milliliters. It wouldn't be fair to do 3 grams in 5 milliliters, but then do 4 grams in 7 milliliters. You get what I'm saying here? So we're going to try to be consistent by keeping the same volume of water every single time. That's a control variable. Okay. Manipulated variable is something that you change. You can actually still visualize it from this chart here. What are we changing every time? Say it. Yeah, the amount of solute, right? In trial 1, we're using 3, then 4, then 5. Okay. The responding variable is then what are you measuring when we're done? What's the goal of our lab? What are we trying to measure? Temperature, right? We're trying to figure out at what temperature are we saturated. Does that make sense? So we're going to manipulate the amount of solute in a constant control amount of solvent, and when we're done, the responding variable will be what temperature that manages to be saturated at. So, okay, here's another question that's almost on every lab. I'm going to ask you about accurate and precise measurements. Yeah, I'm still good for a little bit here. Okay, do I need to give a quick review about accuracy and precision, or do you guys feel like you know those words? Okay, let's talk about tools then. One of the tools you guys are going to use tomorrow is a pipette. You guys remember a pipette? It was a thin little tube with a little bubble in it. Okay, it is precise to 5.00 milliliters. That's how precise it is if you draw water up to the line, and that's the if. How accurate is it? Depends on how good you are. right? If you're supposed to draw water up to this line right here, but you accidentally draw it up to here, you were not accurate. Does that make sense? Precision depends on how good your tools are. So the pipette is actually precise to this digit, but when you talk about accuracy, you're going to have to talk about how well did you actually use the tool. Does that make sense? Let's say you're using a scale. The scale is probably accurate so long as it's been calibrated properly, but its precision depends on how many decimal places it gives. So if the scale goes to the nearest tenth, that's not as good as to the nearest hundredth or thousandth. Here's another thing you guys can work on before tomorrow. Can you guys discuss these terms? Saturated, unsaturated, and supersaturated? We just talked about that today. Here's another one. 3 factors which affect a solvent's ability to dissolve a solute. Also, right out of our notes today. Here's another question I'd like you guys to do. Every lab, I'm going to ask you guys to do a little research on an MSDS sheet. You guys know what MSDS sheets are? Which basically tells you all of the safety considerations. And I can't say that you have to do this first, but it sure would be nice if you guys did this. In case something goes wrong tomorrow, it would be nice to know, like in section 3 of an MSDS sheet, which, by the way, they're super easy to Google online. Literally type in potassium nitrate, MSDS, you'll find one. Okay. And it lists all these sections. Here's one thing I'd like you to figure out. What organs does potassium nitrate cause toxic effects to? Because tomorrow we're going to be working with the toxic chemical. So let's not bring food tomorrow, by the way, because I don't want you to ingest this by any means. Or here's another thing you might want to look up here. What are some of the side effects with inhaling potassium nitrate? Or another one here. What are some side effects involved with ingesting potassium nitrate? Okay. I'd like you guys to be aware of what chemicals you're working with before you use them, because I'm not going to baby you guys. We're going to use real stuff. But sometimes real stuff is poisonous, corrosive, toxic. So if you could can you guys read through the lab real quick and maybe take a look through that question? It's super easy, by the way. Like, I'll do one of them right now, and then I think I'll let you guys go here. If you were to just Google potassium nitrate MSDS, there's one company that I usually go to. It's called sciencelab.com. It's almost always the first one. And this is an MSDS sheet. It's really easy to read through. It literally lists them in sections, and I will tell you which sections to look for. So, like, for example, in section 11, toxicological information, if you just scroll down here, I'll give you one of the answers then. We were going to look for, what did I ask you for? Side effects for ingesting potassium nitrate. And if we read here, see how it says ingestion here? Here's some of the stuff that would happen if you ate it tomorrow. And please don't eat stuff in the lab. It would cause violent gastroenteritis with nausea, vomiting, and severe abdominal pain, colic, diarrhea. Yeah, don't eat this. It's bad for you, Another thing that sometimes is useful, I didn't ask you on it, but sometimes it's good to know about things like first aid measures, like what happens in case of skin contact, what happens in case of inhalation. Right. So anyways, hopefully that gives you some more stuff to work on. So tomorrow we're going to do a lab, and then Thursday we're doing a quiz. Sound good? So start on the lab, though. You can. Oh, wait, you guys can take off.